We're now moving on to our sponsor today, which is InterSystems, and Jeff Fried. Jeff is particularly passionate about helping people create powerful data-driven applications. He has extensive experience in data management, text analytics, enterprise search, and interoperability. He has authored more than 50 technical papers and co-authored 3 technical books. So today, Jeff will talk us through the pros and cons of the different approaches to data storage. I would also like to thank InterSystems for sponsoring the event, as I said before. So without further ado, ladies and gentlemen, can I pass you over to very capable hands of Jeff.
Good morning. I hope everyone can see me and hear me fine. I'm delighted to join you, albeit virtually from the States, and I'll be talking for this next 20 minutes or so about simplifying data architecture. As architects, undoubtedly, you run into situations where you have a collection of different data stores. And I've noticed a bunch of patterns and will offer some examples I hope are helpful. Mick already introduced me, so I won't spend time on this, other than to say I'm an old guy. I've done many projects and have lots of scars to show for it. About 2 months ago, I was delighted to join one of our customers here in the States in New York to celebrate a go live on a project where they had replaced a combination of Redis and Aurora, that's Amazon Aurora database, with a single data store, which happens to be our InterSystems Iris data platform. That's the one that I'm obviously most familiar with. And they did a postpartum analysis of the project, which had been running into performance issues, which is what caused the switch to begin with. And by replacing a combination of this in-memory cache layer in front of a SQL database, which is a pretty common pattern, with a single data fabric, they clearly simplified things. So, 2 moving parts to 1. But they also decreased the CPU load by a factor of 2 and improved performance by about 50%. And this is the kind of example that I'll be taking you through in 3 different patterns. The first is a pattern that I'll call a multi-model database, where instead of a collection of special purpose data stores, a key value, a document database, a graph database, you're able to consolidate those into a single multi-model database. The second is a extremely common sort of textbook pattern of separate transactional and analytic data stores that can be combined or simplified. And the last is a combination of machine learning platforms and data management platforms. So let's get into it first with the multi-model database. And when I'm talking about data models here, it's a little bit different than you might do in, let's say, an Irwin data modeler, which is all relational. There's different kinds of underlying data structures that are used for these different families, such as a document database, or something like Neo4j is a common graph database. There's roughly 370 databases on the market. About half of them are open source, and there's just a huge flowering of innovation but it also creates a lot of confusion, and many developers pick their favorite pieces and then glue those pieces together. Because as you're developing applications, you often find that you need multiple data models. This is a great book I would recommend if you want to know more about this data modeling with multi-model databases from O'Reilly, but they use an example from Airbus where the fleet management application needed both a document data model to store each thing because the dimensions of each thing are different. And then contain those into a graph so that you can look at the relationships between, let's say, landing gear and the fuselage with some relational capability in order to look at roll-up reports and analytics, and also time series for maintenance intervals. So this is at least 4 different underlying models, and that's a fairly common pattern. I did an analysis along with a colleague from a company called ArangoDB of a hotel booking application. And this is something which used 5 different underlying data stores, as you can see on this slide. A combination of Redis for session data, MongoDB for the documents for a product catalog, recommendations and ratings being held in a graph database. They use Neo4j, financial data, relational stuff in MySQL, and then last but not least, a search capability built in Elasticsearch. So 5 different data models, and therefore a fair amount of complexity. And we compared side by side this structure, which is often called polyglot. Polyglot persistence is a fancy term for use of multiple data stores together in a single application versus a multi-model single data store. I'll say about of the many databases out there, there's about 24 that handle multi-model well, and there are variances between that. In this case, I compared it with the InterSystems Iris data platform, which is natively multi-model. And because of what I just described, if you look at the difference in product variety, there's fewer choices. There are mainstream choices, for sure, but not the 360 different varieties. And a multi-model database may have most, but not necessarily all of the features of each underlying data model as compared with a collection of specialty stores. If you look at things from a deployment perspective, there's a situation where 5 different systems versus 1 is obviously more complex and hard to deploy, but it becomes even worse when you consider things like high availability, because each of these data stores has their own model for scale out. So both when it comes to scaling for load and scaling for HA and disaster recovery, you take the complexity of 5 moving parts, and that compounds. In this case, it takes 13 instances to provide a high availability store in this particular application. And you need to synchronize data between these separate moving parts. which means that there's data duplication, which means that there's lots of ways that things can go wrong. And that means that the application is more complex. Often that means it takes more time, certainly it takes more testing. Often these applications are brittler than I think they need to be. And as architects, I find often this is a situation that you get into because developers have chosen whatever their favorite thing is, and then you need to reuse that data in a different application, and it's particularly hard. You also need to learn multiple products, be able to debug and support multiple different products, and then the total cost of ownership increases. So we did an interesting exercise. We took this application and asked the development that it was an outsourced development. We asked them to do their best apples to apples comparison from what they had designed in open source versus what they designed for InterSystems Iris. And there's a lot more data about this. If you're interested, let me know. They did a really interesting write-up. But the complexity of the Polyglot application you can see here in the blue. There's about 9 times more associated libraries, drivers, helper classes, etc., and about 7 times more time spent researching how to do things. The configuration is much more complex, and the total cost and cost in most software applications is mostly about people time, not license cost. But even factored in the license cost of InterSystems Iris versus, in this case, counting nothing for open source, even though typically for production applications, you'd want to have some supported version of open source. There's a factor of 3 in development time and cost savings by simplifying the architecture. From a performance standpoint, this is where you would naturally think that a best of breed approach, a polyglot approach, would be better because each data store is highly optimized for performance typically, and you can do some work in parallel. But it turns out even on direct single applications on different models, a multi-model store can be pretty much as fast as a specialty. In this case, the blue is a graph and the brown is a document data model, and the green is a multi-model database. So not always fastest. For example, you'd expect a graph data store to be great at something like a shortest path algorithm, but definitely competitive. And then when you combine them into an application, much like the financial services application I opened with, the latency between the moving parts adds delay. And there's another interesting factor, which is that if you have multiple data stores, they each cache data. But if you have a single multi-model database, that cache is shared across all models, if you will. So you have a higher locality of reference. And the net result is that performance is as fast, if not faster. If you would like to know more about multi-model, definitely contact me. I have a lot of material, and much of it is published and posted. And there's also some great books and technical references from many other people in the field. I would warn you that since I started talking about this about 3 years ago. Now, essentially every major database claims to be multi-model and has, in fact, support for multiple models. And I would look a little closer under the hood if you're comparing, because some of them are natively built and some of them are essentially polyglot under the hood. They tend to have performance that correlates with their origin. For example, the Microsoft CosmoDB came from a relational standpoint and is strong at relational, but weak at most other models. Okay, so we've talked about the multi-model database pattern. I'm going to take the same ideas and translate it to another pattern that I see quite frequently. And this is the combination of transactional and analytic data stores. Sometimes these are also multi-model, but for most purposes, these are straight relational databases, the kind of thing you might have learned about in your data management graduate class or something like that. There's not a common term for this. Forrester calls this translytical, which is sort of a lyrical term. Gartner, another industry analyst, calls it HTAP for hybrid transactional analytical processing. You'll see this in a number of academic books and papers as hybrid OLTP and OLAP, but the idea is all the same. It's to have a unified data store that is capable of transactional things. Typically, this involves having locks, being able to roll back, having two-phase commit, etc. That's an operational data store, usually is both transactional and able to do ongoing operations and light reporting on it. Analytical is typically considered more of an OLAP thing, even though the days of cubes are sort of numbered as BI tools have gotten much stronger. But the things oriented towards low selectivity, by which I mean if you have a billion records, a transactional system will typically be looking at one or a dozen at a time. And an analytical system might be looking at 10% or 100 million at a time. And that's why things like column stores are widespread for analytical purposes. What I see happening a lot in the industry are this kind of sprawl, if you will, where there are multiple operational systems. Often there's a data warehouse with some staging data mart, combining multiple things with separate metadata and master data systems, and then layered on top of it some data lake or data swamp, where to me, really the difference between a data warehouse and a data lake is a governance question. Both of them are taking a lot of data in where you're not exactly sure what you'll be doing with it later. So you're storing things for flexibility, but data lake pattern is often a structure or schema on read. Data warehouse is often schema on write. But any way you look at it, this is a complex system. And the same kind of factors that I talked about with multi-model apply here in spades. The more moving parts, the more complex the system. There's lots of data redundancy, the need to synchronize the data. A lot of things go wrong. Typically in a data warehousing system, you have a lot of ETL processing, and this becomes not just a a profession or a job of its own, but the majority of many analytic projects is this ETL. I visited one of our customers also in the state, a group called Medtronic, that was trying to establish data as a service within their organization. And they said that 90% of the work was reformatting the data, recreating a different schema for a different purpose, and they thought they'd reach a asymptote, but never did. So the downside of using separate systems is this extra work and extra complexity. We work a lot at InterSystems with the top financial firms. Credit Suisse is an example customer that simplified their order processing system using this kind of technique. They took multiple systems, combined them to a single one. This is definitely more transactional, processing billions of trades and orders per day, but it also has an analytical side because they have a plethora of compliance reports and governance reports. And in financial services, in many other domains, we work extensively across the planet in healthcare. You see this pattern where you have transactional systems, and then you want to do analytics for insight. So you're looking over the history of things, and you also want to do analytics for governance. And the complexity of adding in multiple separate systems for that versus being able to use historical data along with current data, it makes this kind of pattern a big win. In Credit Suisse's case, they had an improvement in reliability and in resilience, a dramatic improvement in their performance, and a lot of reduction in operational costs by simplifying their data management approach and their architecture. Now, there isn't really a great reference benchmark for this kind of setup. There is a suite of standard, what's it called, TPC, transaction processing benchmarks in the industry, including one that's for this hybrid case called TPCH. But first of all, in my experience, I don't recommend depending upon any benchmark, including what I'm going to just offer to you. But it hasn't been something designed for this sort of translytical approach. We've published in open source a benchmark with data and also a test fixture and results against the major databases that's aimed at this simultaneous queries and transactions. And I've posted a link here that you can look at that includes results as well as it's a way you can plug in something that is based upon your own workload and look at the potential effect of different data stores in your model. So I've talked about multi-model databases and combining multiple data models into one. Also talked about this sort of translytical pattern. I'll very quickly go through a new pattern I'm seeing about doing machine learning next to the database. And what I see, frankly, is many, many applications for machine learning and a huge amount of hype, but a big struggle. There's a lot of roadblocks in getting to production. There's even a lot of roadblocks in getting models that are properly built and transparent and explainable and also effective, and very few shops actually monitor their models for sort of the organic nature of them as the situation evolves. And that results in, it's the result of a lot of challenges. It's hard to find, hire, and retain data scientists because it's a sort of this specialty, weird job. It's difficult to operationalize that, in part because the tooling is complex and you have often multiple pieces. And there's a big move to automating machine learning, in particular, something called AutoML, but you still need to work across multiple systems to use it today. And InterSystems has recently, in October, released a facility called Integrated ML, which embeds machine learning right next to the data. We partner with or provide multiple options for AutoML, both a default one that's built with open source, but is kept sort of white box, very few choices, quick to get going. An open source thing called H2O, which is all of the knobs and anything you would potentially want to change, and a commercial partnership with a company called Data Robot, which has best of class technology, but also a stable of customer-facing data scientists to help customers that may not have the skills or may want to get training. And we've exposed that using SQL. So if you know SQL, you can do machine learning. If you go in and you take a look at this in action, I'm showing a case here where I'm looking at all of the data in a table of breast cancer, of tumors, to see if they're malignant or benign. And to create a model is as simple as the syntax on the left. It's DDL, so just like you would create a table, you create a model. The system knows from the dimensions of the table and the data types what's there. You're predicting a particular column, and a lot of the feature engineering or dimensionality of the data is encapsulated right there. To train the model, it's a simple verb, train model, and then you can use it using a predict verb. So taking the top 50 results and looking at those, you can just take a sample to see that there's both malignant and benign tumors. You can use something a little bit more complex, and in this case, I'm ordering by the probability. So I'm looking at a hit list of the patients that I want to attend to right away because they're the most likely to have malignant tumors. Or I can pass a single observation in and get a prediction and do things in real time. So the last verb is something called validate that gets you a sense of the performance of the model, both as you're training and in operations. So you can do model management that way. If you want to know more about this, again, I have lots of information about it, both sort of business-focused collateral as well as a conference paper from a ACM workshop on data management this summer. So we've talked about these three different patterns. I hope that this helps you look at some systems and at some projects and think about how to simplify the architecture by reducing the number of different data stores. And the examples I've used are from our own data store because I work at InterSystems. If you're interested, certainly come visit us or just take a look at any of the material about InterSystems Iris data platform, which handles a lot of the cases that I've talked about, both multi-model and multi-workload, as well as our recent build-in of AutoML. And that's it. I'm open for any questions you may have now, and I'll also be on a panel later this morning. Thank you.